So in this video, we're going to talk about how to describe characteristics of rational functions. So remember continuous functions? A continuous function is one that you can draw without ever lifting your pencil from paper. So for example, if I was going to draw this function here, I can put my pen on the paper once and then just trace out this curve. So I don't have to actually ever lift up my pen. In a continuous function, the points are all connected. So rational functions are discontinuous. So that's because they have a discontinuity anywhere that the denominator equals 0. So notice in this example, we have y equals 1 over x. So the denominator will equal 0 at x equals 0. So that's why the function has like two pieces. You can see that it keeps going here, right? So this is one continuous piece, but then it kind of breaks at x equals 0, and then I have another piece. So rational functions will be discontinuous. Rational functions also have what are called asymptotes. So you can have vertical and or horizontal asymptotes. So for example, this function has an asymptote at x equals 0, and it also has a horizontal asymptote at y equals 0. So let's graph g of x equals 10 over x and find the domain, range, and asymptotes of the function. So you can graph this function by entering it in Desmos, or you can fill in this table like the one I have here to figure out each of the points. So we have 10 over negative 10, which is negative 1, 10 over negative 5, which is negative 2, 10 over negative 1, which is negative 10, and then 10 over 1, which is 10, 10 over 5, which is 2, and 10 over 10, which is 1. So now let's go ahead and plot these points on our grid. So we have negative 10, negative 1, negative 5, negative 2, negative 1, negative 10, and then we have 1, 10, 5, 2, and 10, 1. So we can go ahead and connect these points to form our graph. So our graph will look like this. Notice that it kind of breaks at x equals 0, right? Which makes sense because x equals 0 will be an asymptote of our function since our denominator cannot equal 0. So that's why we have our function like this in two pieces. So remember, the domain will be all the possible x values of a function. Range is all possible y values. So if we talk about this function, so you can see here now I have the screenshot from Desmos. So this is that g of x equals 10 over x that we just graphed. Notice that the domain is going to include all real numbers, right, up to 0. So we could say from negative infinity to 0. And then there's a second piece that goes from 0 to positive infinity. So we would say and. In math, the way we say and is using the union symbol, which looks like that. Okay, so we'd say and it goes from 0 to infinity. The range also has a similar pattern, right? It goes from negative infinity to 0. So we would say negative infinity to 0. And it goes from 0 to infinity. So now let's talk about the asymptotes of the function. So the asymptotes are not already on the function, they're lines that we draw in ourselves. So a vertical asymptote will occur in an x value that the function approaches but does not actually cross. So for example, this function pictured here has a vertical asymptote at x equals 0. It gets really, really close to x equals 0 but doesn't actually cross it. It'll have a horizontal asymptote at y values that the function approaches as x approaches positive and negative infinity. So the horizontal asymptote kind of tells you a little bit about the end behavior of the function. So you can see here this function as x goes to positive infinity, it approaches y equals 0. And as x approaches negative infinity, it also approaches y equals 0. So y equals 0 is the horizontal asymptote. So let's graph g of x equals 10 over x and find the domain, range, and asymptotes. So we already talked about the domain and range, so let's look at the asymptotes. So notice that it's going to get really, really close to x equals 0, but not actually cross it. So we would say it has a vertical asymptote at x equals 0. It also tends to y equals 0 as x approaches positive infinity and as x approaches negative infinity. So we would say there's a horizontal asymptote at y equals 0. So now you can go ahead and pause the video and try this example on your own. So when you graph 5 over x, this is what the graph looks like. So the domain is going to go from negative infinity to 0 and 0 to positive infinity. The range will go from negative infinity to 0 and 0 to infinity. The asymptotes will occur at x equals 0 and at y equals 0. So we can also find inverses of rational functions. The steps are going to be the same. We're going to start off by replacing f of x with y, then we're going to switch x and y, and then solve the equation for y. So let's find the inverse of f of x equals 6 over x minus 1. So we start off by saying y equals 6 over x minus 1. And then we're going to switch x and y. So we would say x equals 6 over y minus 1. So now we need to solve this equation for y. So the way to do it is I'm going to set this x up as a fraction. So I'm going to do x over 1. So then we're going to cross multiply. Okay. So when we cross multiply, we get 1 times 6, which is 6. And that equals x times y minus 1. So now we need to get y by itself. So we're going to go ahead and we're going to divide both sides by x. So when we do that, we get 6 over x equals y minus 1. So now we're going to add 1 to both sides. So when we do that, we get 6 over x plus 1 equals y. Okay, that is the inverse function. So notice that when you have a rational function, the inverse of a rational function is another rational function, right? So we don't find the inverse and then find a whole new type of function. The inverse of a rational function is just another rational function. So we can also talk about the intercepts of a function. Remember, the x-intercept will be anywhere the graph crosses the x-axis, so intercepts will have the form x0. The y-intercept is where the graph crosses the y-axis, so they'll have the form 0y. So let's find the domain and the x and y intercepts of the function f of x equals 2x minus 6 over x squared minus 4. So I started off by graphing this in Desmos, so let's go ahead and figure out the domain. Notice the domain here is like in 3 pieces. Okay, so let's go ahead and figure out what those pieces are. So there's going to be like an asymptote anywhere we have our denominator equals 0, right? Where our denominator is x squared minus 4. So if we set that equal to 0, remember we can solve that by factoring. X squared minus 4 is basically x squared minus 2 squared. So that can be factored as x plus 2 times x minus 2. And so what we're going to do is we're going to set each factor equal to 0. And when we do that, we get x plus 2 equals 0 and x minus 2 equals 0. So when we solve each of these miniature equations for x, we get x equals negative 2, and we add 2 to both sides, and we get x equals 2. So that means we're going to have vertical asymptotes at x equals negative 2 and at x equals 2, right? Just like what's seen in our graph here. So when we describe the domain, we're going to say the domain goes from negative infinity to negative 2, and it goes from negative 2 to 2, right? That's the second piece right here. And then it goes from 2 to infinity, okay? Right? We have 3 pieces in our domain, right? 1, 2, 3. So that's how we describe the domain of this function, okay? So remember to always think about any asymptotes that you have when you're talking about the domain of a rational function. So now let's think about the x-intercepts. When you want to find the x-intercepts and you're in Desmos, it's very easy to find them because you just have to click on the point where the graph crosses the x-axis. So in this case, if you click on this point here, you'll see that it has the coordinates 3, 0. So the x-intercept of this function will be at 3, 0. If you want to find the y-intercept, you can do the same thing. You just click on the point where the graph crosses the y-axis, and so it's going to be 0, 1.5. So that is the y-intercept of this function. So we also have something called a point of discontinuity in some rational functions. These don't happen in every rational function, but they do happen in some. So what they are is a hole that you'll have in a graph. They're also known as removable discontinuities because if they were filled in, the graph would be like one piece on one side. Okay, so you can see here, like this graph has a hole right here at x equals negative 1. If it was filled in, this graph would continue like this, okay? So that's why it's called a removable discontinuity. So how do you determine if you have a vertical asymptote or a hole at a specific x value? If a value of x makes only the denominator equal to 0, okay? So like kind of like what we did here. We set the denominator equal to 0. So if it makes only the denominator equal to 0, then it's going to be a vertical asymptote. If it makes both the denominator and the numerator equal 0, the graph will have a hole, okay? So how does it make both equal 0? Well, I'll tell you what happens. It'll be a common factor that you have in the numerator and denominator, okay? So for example, if you have like x times x plus 2 times x minus 3, okay, and that's over x plus 2 times x plus 4, okay? This rational function, do you see that repeated factor of x plus 2? It's going to have a whole at x plus 2 equals 0, okay? It's not going to be a vertical asymptote. It's going to be an x equals -2. You're going to have a whole at that point, okay? So that common factor is going to be a whole, but this factor that's just in the denominator, that is going to be the location of a vertical asymptote. So that's the difference between a vertical asymptote and a whole. So how do you determine horizontal asymptotes, right? Remember, those are those asymptotes that go across like this. Well, what you have to do is you have to look at the degree of the numerator and the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. Okay, so look in this example. So we have the degree of the numerator is 1, degree of denominator is 2. Okay, so we have numerator less than denominator, so that is why it's y equals 0. If the degree of the numerator equals the degree of the denominator, the horizontal asymptote is a over b, where a and b are the leading coefficients of the numerator and denominator. Okay, so you can see in this example we have an x squared and an x squared. So you're going to do y equals 4 over 2, okay, the ratio of the leading coefficients. So y equals 2 is the horizontal asymptote. If the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Okay, so you can see here I have degree 3, denominator I have degree 1, okay? So since numerator is greater than denominator, I have no horizontal asymptote. So let's find the domain range asymptotes and any discontinuities of f of x equals x plus 1 over x squared minus x minus 2. So always it's a good idea to start off by graphing the function. Okay, so when you're finding all this information, I think it's helpful to start off by finding the discontinuities. Okay, by discontinuities, I mean holes and vertical asymptotes. So what you need to do is you need to factor the numerator and denominator. Okay, so the numerator is x plus 1, so we're just going to leave it alone. I'm going to factor x squared minus x minus 2. Okay, so I need two factors of -2 that are going to add up to -1. Well, my -2 is negative, so I need a positive and a negative factor. My 1 here is negative, so I need my bigger factor to be negative. The only factors of 2 are 1 and 2, so I'm going to make that 2 negative, and 1 plus -2 is -1. Okay, so that means that my factors are x plus 1 times x minus 2. So when we factor this function, we have that f of x, so f of x equals x plus 1 over x plus 1 times x minus 2. And look here, we have that common factor, right? So at x plus 1 equals 0, I'm going to have a hole in my function. Okay, so that is going to be where x equals -1. So how do I figure out the y value, right? The hole is a point, so it's going to have an x and y value. So what I'm going to do is I'm going to write the reduced function, okay? So I have f of x equals 1 over x minus 2. And what I'm going to do is I'm going to plug in -1. Okay, so I have 1 over -1 minus 2. So that's -1/3. Okay, so my hole is going to occur at -1, -1/3. Okay, so that's one of my discontinuities. Now I need to figure out my vertical asymptote, right? Vertical asymptotes in another place the function is discontinuous. Well, to find the vertical asymptote, what I need to do is take what's left in the denominator and set it equal to 0. So I have x minus 2 equals 0, which tells me I have a vertical asymptote at x equals 2. Okay, so I've identified two discontinuities in my function. Now let's talk about how you find discontinuities in Desmos, okay? So be very careful. So you can see here, here's my screenshot from Desmos, okay? Notice it doesn't show you the hole, right? We don't see the hole as like an open circle like it does in textbooks. So what happens in Desmos is if you click on that actual point, like we discovered at -1, there should be a hole. And if you click on the actual point, it'll show up as a hole. Okay, so notice that when I clicked on it, it said -1 undefined. So you just have to click on that point to see it. Just because it doesn't show up in Desmos does not mean that there's not a hole there. So let's talk about vertical and horizontal asymptotes. Okay, so back here we already found the vertical asymptote. That is going to be at x equals 2. And now let's talk horizontal asymptote. Okay, so we need to think degree of numerator, degree denominator. Okay, so in this case, the degree of the numerator is 1. And that degree of the denominator is 2. So degree numerator is less than degree of denominator. So that tells us that we have a horizontal asymptote at y equals 0. So now we have all this information. Now we can go ahead and describe the domain and range, okay? So the x values are going to have a few places of discontinuity, right? We have this hole at -1, -1/3, and x equals 2, okay? So I'm just going to write those values here just so we can remember. And then we have x equals 2. Okay, so what happens is we're going to go, domain goes like smallest to biggest, right? So we start off at -infinity, and then the graph is going to go to -1, right? And then it's going to stop there. And then what we're going to do is we are going to say, then it goes from -1 all the way to 2, right? 2 is the next place we have a discontinuity. And then it's going to start up at 2 again, and it's going to go to infinity. Okay, so it's going to go here. It's going to stop at this hole, right? There's a hole that we can't see because this is from Desmos. And then it goes from here to here, and then it goes from here to here. Okay, so there's 3 pieces in the domain. Now let's talk range. Okay, so it's going to start off at -infinity, and then it's going to go to, let's see, we have our asymptote at y equals 0. And we also have the y coordinate of the hole. Okay, so the y coordinate of the hole is smaller, so we're going to say -1/3. And then it's going to go from -1/3 to 0, right? So it's going to go up to the hole, and then from the hole up to 0. And then it's going to go from 0 to positive infinity. Okay, so we actually have to describe the domain and range in pieces depending on where we have holes and where we have asymptotes. So now you can pause the video and try describing the domain, range, asymptotes, and any discontinuities of f of x. So when you factor this function, notice that we have a common factor of x plus 2, so we're going to have a hole at x equals -2. When we reduce the function, we get 1 over x minus 5, which if we plug in -2 to that function, we get -1/7. So there will be a hole at -2, -1/7. So the vertical asymptote, if we set the remaining factor in the denominator equal to 0, there will be a vertical asymptote at x equals 5. The horizontal asymptote, we're going to look at the degree of the numerator and denominator. Degree of numerator is less than the degree of denominator, so we're going to have a horizontal asymptote at y equals 0. So now let's talk domain and range. Okay, so the domain is going to go from -infinity to -2, right? Remember what happened at -2? We had that hole there at -2. Okay, so then it goes from -2 to 5, right? Because remember, x equals 5 was our vertical asymptote. And then it goes from 5 to infinity because we have no discontinuities after that. Range is going to go from -infinity to -1/7 because that is the location of our hole. Then it goes from -1/7 to 0, okay, because that's where we have our asymptote. And then it goes from 0 to infinity. So when you're describing rational functions, it is very important to think about several key characteristics. You want to think about domain and range, the asymptotes, any intercepts, and if the function has any discontinuities.